Today we're going to look at the topic of mechanics for A-level physics, in particular forces and equilibrium. If you found exam past paper questions difficult on this topic, please stick around to the end of the video. There'll be a couple of walkthrough examples of typical questions that can come up. So the basics then, for an object to be in equilibrium there needs to be zero resultant force, there also needs to be zero resultant moments. So that means the principle of moments must apply, which is that the sum of all clockwise moments equals the sum of all anti-clockwise moments. I'm using the sigma symbol here to indicate sum. So the most easy example to understand is if you've got a seesaw, I've got two objects on either side. If I knew the forces acting downwards from each object and I knew the distances between them, were I to multiply the force by the distance for object 1 and object 2, they should equal each other, meaning the moments are equal. This could happen with multiple objects, but just for the sake of sort of ease of an example here, I've gone with one. Now, the slightly more advanced version of this is if I've got an uneven rod, or it's pivoted, not in the center. So in this case here in the diagram, I've got the pivot towards the left-hand side, and that's because I've got an extra resultant moment acting from the center of mass of the rod or of the ruler. Now, I'm going to label the force produced by that F3, so that's the weight of the ruler acting from the center of mass, but it's essentially like any other force. If I knew the value of it, I knew how far it is from the pivot, I can just include it in my moment calculation. So in this example, I'm going to have two clockwise moments and one anti-clockwise moment, which have to be equal to each other, same as before. The other type of example you can get with moments is one where you've got two support forces. So in this example here, if I've got two supports propping up a bridge or a ruler or anything like that, basically I treat it as if I've got two pivots. So I've got to choose to take moments about one of the pivot points. Now it doesn't matter which one you choose, but it all depends on the situation from which one you take as your pivot. Same as before, you've got to consider the center of mass acting from the center of the bar or of the bridge going downwards. And once you've chosen a pivot point, so in this case I'm taking the one on the left as the pivot point, I can just do moments like before. So I've got F1 D1 plus F3 D3 equals the anti-clockwise moment, which is F2 D2 in this case. So it's just about trying to simplify it and treating it as a normal sort of moment situation. Now, last thing to sort of know about here is what a couple is. So a couple in physics is a pair of two equal and opposite forces which act not along the same line of action. So the clearest example is the one here. You've got F2 going sort of up and left, you've got F1 going down and right, and they're both going to work to rotate that system about its axis. So they're in opposite directions, but not on the same line of action, if that makes sense. How you'd work it out is you work out the moment equals the force times by the distance between the line of actions of the forces. So it'd be F1 times by D in this instance. Okay, now as well as sort of looking at moments, you could be asked with equilibrium to look at forces in a bit more detail, forces at an angle. I thoroughly recommend watching my video on resolving using trigonometry, absolutely essential for A-level physics, but you could be asked to do them to scale or to look at force triangles to help explain a situation. So in this example here, I've got a slope, I've got the weight acting downwards, and now I need to be able to sort of prove, let's say without numbers here, that the forces are balanced. Okay, so here we've got the weight of the object going directly downwards. We've also got the reaction force acting perpendicularly away from the slope, and when we've got the friction force going up the slope. Now let's assume the object's in equilibrium, so it's either travelling at a constant velocity or more likely it's going to be stationary in this scenario. Well, that means if I was to draw all the force arrows tip to tail, they would form a closed triangle, which indicates the forces are in equilibrium. If there is a small gap between any of the sort of tips and the tails of the arrows, it shows there's a resultant force. So here I've got a little gap between the tip of F and the tail of W, meaning there's a resultant force, which means the object would actually be accelerating. Let's have a look at some exam questions to help understand this topic a little bit better. Let's see if we can put all our knowledge about equilibrium and moments, etc., into practice with some exam questions. We've got a meter ruler here, which tells us the weight is 1.5 newtons and it's pivoted 15 centimeters from the end. We've got a pan, which weight we do know is 0.5 newtons, and we've got object of unknown weight, which I'm going to label as X. We also have another weight at the end, which we do know the distance, it's 60 centimeters away, and the question is basically what is X, what is the weight of the object here. So first thing is to do is to set up sort of clockwise and anti-clockwise moments. So I like to do those sort of just using the arrows here. So in terms of clockwise moments, the obvious one here is I've got 2.5 newtons weight and that is in meters, 0.6 meters away from the pivot. Now, the one they don't tell you directly is that also, because it's a meter ruler, it will have a center of mass. So the center of mass is where the weight of the ruler will act from, and here that is 1.5 newtons. Now, how do you know how that relates to where the pivot is? Well, the pivot is 15 centimeters from one end. It tells us it's a meter ruler, so therefore this distance here has to be 35 centimeters or 0.35 meters. So don't forget about the center of mass of the ruler. That's the one thing that could easily catch people out in this question. So that's also going to produce a clockwise moment. So we've got 1.5 newtons times by 35 centimeters. And now, principle of equilibrium to apply, that means that has to be equal to our anti-clockwise moments. So anti-clockwise moments is going to go this way. That's basically just the pan and the unknown weight acting on it. So that's going to be equal to the pan, which has a weight of 0.5 newtons, added together to our unknown weight, because they're both exerting the force in the same place. So therefore we say it's 0.5 plus x, and that's going to be, I'm going to do another bracket here, times by the distance, which is 0.15 meters. So that's our setup. Next we got to do is find x. So it depends how you want to do things on your calculator. You can always plug them all in and then sort of work out x from there. I tend to sort of make things a bit simpler when I'm doing workings out, so it makes my life a bit easier. So basically what we've got down here, if I do 2.5 times by 0.6, that equals 1.5. And then if I do 1.5 times by 0.35, that happens to be 0.525. Then that equals what's going in the anti-clockwise direction, which it kind of stays as it is for now, so 0.5 plus x, which is going to be times by 0.15. Just going to write that down here. So how do we find out where x is? We need to get out of this bracket first of all. So the first step is to divide everything by 0.15. And then we're left with 0.5 plus x. So to find out what x is, once I've worked this bit out here, I just subtract 0.5 from this on the left to find out what x is. So I'm just going to rewrite this slightly down here. So I've got this whole expression minus 0.5. That take away from that expression gives me what x is. So you put all those numbers into your equation, and you should find the weight we're looking for is 13 newtons, which is one of our options. That's option C, which is the correct answer for this question. Right, for our next question, we've got another uniform rod. It doesn't tell us how long it is this time, and it's one of those which statement is correct questions. So either the rod in equilibrium, or there is a moment needed, or there is an additional force needed. So for equilibrium, we need there to be the sort of sum of the moments is equal, so therefore sort of clockwise equals anti-clockwise. So we're going to check out that first, and then we need to know, we need to consider the forces as well. So we'll come on to that a little bit later. So is it in equilibrium? Now there's a lot of information here to sort of take in, and there's no obvious pivot point. However, there are two forces here acting from the same point, so from the center of the ruler. So we're going to call that our pivot point, and all the other forces can go either side of it. Just makes our life a bit easier. So let's do our clockwise moments first. The one's going this way, and we've only got one, because that pivot, there's no moment, there's no distance. We don't consider those forces to be exerting a moment. So I've got 4 newtons times by the distance it is away, which is 0.2 meters. And the left hand side, we've got 6 newtons times by 0.3. Now, hopefully we can see from here, that's 0.8, this is 1.8. That means that they are not equal to each other. There must be something we need to add on to the left-hand side. Okay, so automatically we can say it's definitely not in equilibrium. We just need to know what to add. So what to add? Hopefully it's obvious it's one of these two options here, B or C. So is it anti-clockwise or is it a clockwise moment? We know it's going to be 1 because x plus 0.8 makes 1.8. Hopefully we can figure out it's got to be a clockwise moment for this to work out, because it's missing from the clockwise section we were working out earlier. So it is part C, option C, that is correct here. Now, why is it not option D? Well, if you consider the forces, we've got 20 newtons upwards, 10 newtons downwards in the same spot. We've also got 4 newtons downwards and we've got 6 newtons downwards over here. Now, regardless of where they are, when we're considering forces in the same plane, i.e. linear to basically in one direction, as long as those are equal, it doesn't really matter where they are. Okay, so I've got 20 newtons up, 20 newtons down, so it's an equilibrium from the forces point of view. It was just from the moment's point of view we had to work out something a bit different. We're in a fairly similar situation with this next question, and we've got another uniform rigid bar, no value given us about its length, forces acting on it, which side shows, which letter shows the bar in equilibrium. So we've got to look at moments, and we've got to look at forces to see if that thing is the case. So let's have a look at sort of each one in turn, and then go from there. Now, the most obvious point would be to look at forces, I would say, because I think it's just easier to add the forces up. So let's do, we've got upwards, we've got 10 here, downwards we've got 10, so that one could be in equilibrium. We've got 8 downwards here, but we've got 10 downwards here, so we know it's definitely not going to be B. Next one, we've got 2, 2 and 4, so I've got 8 going down, and again I've got 8 going up, so it could be this one here. We've got down this one here, we've got 2, 8 and 2, I've got 4 and 4, so we know it's not going to be this one over here. So we can discount sort of B and D quite early on to make our lives a bit easier for these ones. Next, we've got calculate moments. So again, it's kind of up to you where you want to decide where the pivot's acting from, where the pivot is. I would just use the center if in doubt, unless there's a reason to. We've got 2 forces acting in opposing directions. It doesn't matter if they're even or equal or not. So for this one, so left-hand side, we've got 2 newtons going in the clockwise direction. We don't know the distance, but we can just call it x, whatever. It's going to be the same this way. And we've got 2 newtons, don't forget. So we've got 2 newtons going in this direction, but we've got 4 newtons going in this direction. So if I was to sort of work out this one, I'd say clockwise, I've got so 2 newtons, so 2x, this one here, and I've got 2x going this one here, and then I've got 4x, this one here. Now hopefully that's obvious, those two definitely are equal to each other, so it is going to be A that's in equilibrium. Let's just double check we know why it's not C. So in this one I've got pivot point from here, I've got, let's say, so this is for A, this is for C, I've got 4, let's say 4x going sort of clockwise, and I've got another one going clockwise, which is another 4x, so this one here. So we've done the 2 4s already. And then anti-clockwise, I've got this direction here, so I've got equals 2x, and then I've also got this one going anti-clockwise, which is another 2x. So you've got to keep an eye on directions here, okay? Those two are both going clockwise, and these two anti-clockwise. Hopefully you can see those are not equal to each other, so therefore it's not going to be C, so therefore it's going to have to be A. Right, I hope you found that useful. Obviously there are more equilibrium examples in exam questions. That was just a little flavour of some multiple choice ones that have come up on the AQA spec. I hope you found that useful. Please leave it a like if you want to see more of this kind of content.